All right, welcome to lesson 5, underfitting and overfitting. The big idea about this lesson is that when we train our model, we want to give it enough training so that it can have time to pick up and find all of the different patterns and features in our data so it can make really good predictions. When you underfit, you don't give it enough time to do that. So it ends up missing some of the patterns that it could have found. Overfitting is the exact opposite. It's when you keep training the data for too long and it gets so used to that training data, when you give it new data, it kind of doesn't know what to do with it. 'Cause it's like, well, it doesn't really fit. Like I have such a rigid structure to my brain. I can't fit new data into it. I don't know where it goes. So it does a bad job predicting new stuff. So what we're looking for is somewhere in the middle there, where the learning has had enough time to find the patterns it needs, but not so much time that it's over-specified to that data. It can still take in new data and handle it when it does predictions. That's a little confusing maybe right now, especially the overfitting side of it. We'll see more of that as we go through. All right, of course, we've been working with what are called decision trees, which are these like yes-no decision trees that flow down. In this, we call layers of the tree. We call, every time we have a yes-no break, we call those a layer of the tree. So this has 3 layers in this tree. And these ending points here, where the last step in them, these are all called leaves in the tree. So you can see there's these branches going around here. And at the end of the branch is a leaf. So one of the things that we can do, so for example, this one has 4 leaves. What that means is, if you were building a very simple model like this, it would force all the houses into one of 4 buckets, depending on how it handled these branches. And because we're sitting in more than just like 2 features like this first break might be like, does it have 2 bedrooms and more than this square feet and this and this and this and then this? It'd be a bunch of criteria. It'd be a yes or no. Excuse me. And that would direct it down to another one with some criteria on it, and then it would flow into those leaves. What it would do after it flowed all the houses into a particular leaf, and it wouldn't have to be like a quarter here, a quarter here, a quarter here. It could be some over here, fewer here, a bunch here, wherever, however it worked out. It would take all the values of those houses, average them together, and then set that average value to these numbers here, and that's the predicted price for that leaf. So then when you put new data in, that data will follow the tree around, each house will fall into a particular leaf, and then that house will be assigned the average value in that leaf. So here you can see these are the only 4 possible predicted values. This probably isn't going to do a very good job of predicting house prices, unless you happen to be like in this area. All right. Now, one of the things that we can do with the decision tree to limit or to control it for underfitting and overfitting, let's do the exact opposite. So this is one with 4, and you can see how there's just too big of a bucket catching all those houses, too many houses in each leaf, too wide a price range in there. If we allow the tree to just get bigger and bigger and bigger until each house gets its own leaf. So it goes through enough combinations and splits and all this stuff so that there's a leaf for every house. What we find is it'll do a fantastic job at predicting the training data, because that house has its own leaf. It goes right into its own exact price. The problem is when you add new data, it's hard for that data to find its way through. And when it does land into a leaf, its only option in that leaf is to be the exact same price as the other house in that leaf. So you actually want to bring it up a couple levels so that there's a bunch of houses in each leaf, so that there's like a range of prices in there. So overfitting would be like too many leaves, underfitting is not enough leaves, somewhere in the middle will be a really nice area. All right. So one thing that we can do in order to control this is, this is a graph I gave here. This axis here is the mean average error. So this is how far off you are. So you can see when you're underfit, your validation scores will have a really high error. So will your training data. So if you run your training data through, as you go through and you allow the model to have more and more and more leaves, So this would be like 2 or 3 leaves here. As you let it have more and more leaves, it's going to fit to the training data really, really well and just keep getting better and better. And this might even go down to 0 where it's perfect at predicting the training data. But here, your validation data will continue going down. You're improving your models, seeing more patterns. But at some point, it's going to start going up again. You're going to start getting more validation error or more error in your validation data because it's overfit here. It's too rigidly stuck to the houses it's already seen. It can't handle new house as well. So don't worry about the exact shape of these curves. We'll talk more about that. Now to see how this works with the code. So again, here for this first part of the code, we're going to be bringing and importing our mean absolute error. This is going to allow us to calculate how far off we are from our actual values. We're going to also import from sklearn.tree, we're going to import the decision tree regressor model. So when we bring this in, we just bring in the ability to build the model. So we import all that stuff to build the model with. Now, I don't like that they did this, but sometimes they make things more complicated than they need to so they can make the code shorter. I'd prefer if they would have kept the code longer for us as we're learning and not done these shortcuts that help us be like concise. But they did, so we have to deal with it. So the first thing they did is they created a function definition. So this code won't run until it's called. So in JavaScript, we created functions by using the function, and then we would name the function and have parameters for it. This is the exact same way, except it uses def or definition to identify that what it's creating here is a function. The name of this function is, the name of this function is getMAE. So MAE is the mean absolute error. So my guess is, if I'm just looking at this function, it's going to actually calculate the MAE for us. The parameters that we send into this function is we have to tell it how many leaf nodes do we want to limit it to. So here, if we wanted to create this simple, terrible model, we would put a 4 in there. So it would limit it to only be able to make 4 leaf nodes. The next parameter we need to send in is we need to send in the training X data, and then the validation X data, and then the training Y data, and the validation Y data. So this tells me that we actually need to take our overall data and break it into training and validation data before we can use this function. So to do some of that test train split stuff before we use this function later on. All right, so that's the name of the function is getMAE. It has 5 parameters we have to send into it. This colon means down below are all the things that are going to happen when you call this function. So the first thing getMAE is going to do is going to create a temporary variable called a model, and that's going to equal here the decision tree regressor. So that's going to take the blank model, the regressor from here, and we're going to tell it the max leaf nodes is going to be equal to this max leaf nodes. So I wish they would have named it the same thing as this one. I wish they had called this max leaves instead of max leaf nodes, because it looks the same. But this is the parameter of the decision tree regressor. This is the way you control the max leaf nodes. So you say, hey, max leaf nodes equals, and then you'd put a number here of like 20 or 30 or 40, whatever you want it to be. In our case up here in this simple model, we would have put 4 in. So we would have typed a 4 right here when we went to use the model thing, and that 4 would have flowed right to there. And then the random state is 0, like we said before. That just keeps us to have a consistent model every time we run the program. All right, next thing we're going to do is, so we've set up the model. We've told it how many leaf nodes it's allowed to create. Now we're going to do a fit of it, and we're going to fit it with the train X and train Y data, just like always. And so now after this line of code runs, our model is fully built. So now we have a fully formed model, and it's stored in this thing called model. Now we need to predict the values. We need to actually go and see how well our model did. So we're going to use model here, which is that fully fit model. We're going to do .predict, and we're going to predict using the validation data like we have been before in the past. So remember, these are houses that the model has never seen before, so it's going to have a fresh look at them to see how well it does. And then we're going to calculate the mean absolute error using the mean absolute error function by comparing the actual Y, the actual sale price of those houses in the validation set with our predicted sale prices. And that will tell us how far off we are. We will store that number, so we'll take an average of all the errors. well, the absolute value of all the errors. And that's going to store that value in this variable called MAE. And then it's going to return the MAE. So wherever we call this function, it's going to return one value, which is how many dollars off we are on average from being correct, on the correct price. All right. So the next thing we need to do is we need to do, so this, we haven't actually done any of this work yet because we haven't called the function. We've just created this function definition that we can use later. All right, so we're going to import pandas. We're going to take our file path, just like we did before. We're going to use the pandas read CSV to convert this CSV file into a data frame that the machine learning can use. This, don't worry about this. This just drops all of the rows of data, the houses that are missing some data parts to them. Otherwise, it's going to throw errors if we don't do this. So we're going to get rid of this. In our Iowa data, we don't have any of that, so we don't have to do this step. We're going to then tell the model, just like always, what are we predicting? That's our Y values. And it's going to be the Melbourne data.price. So that's the column name for this one. And then we're going to set up what features do we want to use to do predictions. Here they're using these, it looks like 7 features here. And we're going to then pull those features out of our main data source. So we've got all of our data up here, and it says, hey, pull out just these features and make a new data frame called X with just those features in there. And then we're going to bring in from the sklearn library, from the model selection part, the train test split function. That's going to do our splitting for us. And again, we create 4 variables here: train X, val X, train Y, val Y. And then we run the train test split function on our X and our Y, and that will do all the splitting for us. Again, we choose a random state so that it will repeat and do it the same way each time we run the code. Okay, so all of that was just a review of what we've done already. So we've split our data up. Now here's where we're going to do something a little differently, and this is a really cool thing. This is a Python for loop. So you start with the word for, and without any parentheses or anything like that, you do some variable here. So for max leaf nodes, that's a new variable you're creating in this list here. So these are the things that we're going to be testing. We're going to test them one at a time. So what it's going to do is, when the first time through the loop, it's going to take this first value in the list and store it in the variable max leaf node. So max leaf nodes will be 5 the first time through. Then the next time through the for loop, the max leaf nodes will be 50, and then 500, and then 5,000. So this max leaf nodes, you can think of it as like the I in a JavaScript for loop. So it's the thing that's going to hold the value every single time. Here we're counting from 5 to 50 to 500 to 5,000. All right, hopefully that makes sense a little bit. The colon here is one of the few times that Python has punctuation in it. So this colon means that everything after this colon that's indented is inside the for loop. All right, so we're going to run this function. So we create a new variable called myMAE. We're going to run this function called getMAE. So that's this one up here that does all of the work of creating the model, setting the leaf nodes, training it, predicting it, and running the error of it. We're going to run that error using max leaf nodes. Now the first time through the for loop, max leaf nodes is set to 5. So it's going to send the 5 in. It's going to send in our train X, val X, train Y, and val Y data that we created up here. Send those in. And then it's going to print this max leaf nodes down here. So notice it prints the words max leaf nodes. And then this is another thing I wish they wouldn't do in this, is use some of this higher end Python code. This %d means you're going to go get this thing over here on the % and insert it in over here. We won't use this when we do ours. We'll make it a little more straightforward. And then so it brings in the first thing, this part. It puts that here. It puts the second thing on the second %d. So it prints the words max leaf nodes and then 5, which is the max leaf nodes for the first round. And then it's absolute error of 34,000. And then the second time through the for loop, the max leaf nodes is set to 50. So this is 50. And this is the mean absolute error for 50 nodes. And you can see by looking at these, you can kind of start seeing, okay, so we start out with a lot of error. The next one we get less error. So that means this one must have been underfit. So this is a better fit, more fitting. We get even less error here. So 500, it needs more time to develop really good patterns. And then here with 5,000, we have an absolute error. It's starting to get worse again. So what's happening here is this is where overfitting is kicking in, somewhere between 500 and 5,000. Now, if we want to really find the best number of nodes, we could now center ourselves on 500 and change these numbers to, like, I don't know, 300, 400, 500, 600, and run them again and see if we can start finding the bottom of that mean absolute error, which would be kind of the best place to be. All right, that's it for this video. I hope that makes sense. I know it's a lot. Keep trying to wrap your head around it.